show the mic, bro.
Yes.
Change slides. Yeah. Okay, well, good morning, everybody, and thanks, DK, for the warm welcome. It's great to be back here one more time. This, I think, is the 7th meeting, and I think either Carl Schultz or I have been here from TACC for 6 of them. We'll talk about last year in a moment. But yeah, this is at least my 3rd or 4th time up here giving the keynote. So, and I took out a lot of the old slides from those keynotes because, one, many of you who are familiar faces have seen them 3 or 4 times at previous talks here, and the students, you're just going to have to pick it up as we go. They got deleted this time, but we did have worked with DK and his team and MVAPICH for a very long time now, and DK mentioned the Ranger system in his introduction. And by the way, DK, I'm starting off late, so the very first sentence you said was we need to stay on schedule. You've been the only speaker and we're running late. I'm not going to make it any better, so I just want you to know that in terms of staying on schedule. But we started working with the MVAPICH team and with DK. We brought up a machine called Ranger in 2008, actually awarded in 2007, went into production in 2008. It was the fastest open science machine in the world at the time. Things were a lot different back then in that it was about 63,000 cores. It was one of the first InfiniBand-based systems in SDR InfiniBand. Back then, Mellanox made all the chips, but the switches and the cards actually came from Sun, which is this company you can read about in history books, which is depressing for those of us who've been here for a while. But we've got absorbed into Oracle some years later. But on that machine, you get the stuff from the vendor, and we got the machine deployed and up and running. And everything works sort of. As they tend to with machines at this scale. But it was 62,976 cores at the time, and launching an MPI job across that many cores took, 30, 35 minutes with the stack from a vendor. So 35 minutes, not seconds, not microseconds, minutes. And then every time a node would go up or down, you'd have about a 30-minute sweep on the network. So technically everything worked, but we knew it didn't work anywhere near as well as it could. And we could make things work a whole lot better. And so starting in the first year of that project in production, we came to the MVAPICH team and said, can't this do better than things are? And we started running, instead of the vendor stacks, the open source stacks, and we got launch time down to a few seconds. Working with the Open Fabrics team, or what became the Open Fabrics team, we got sweeps down to a few seconds. Many things got 100 times better as we started doing that. So based on that experience, we made the MVAPICH team a formal part of the Stampede project, a machine probably a number of you used, that began in 2012 and 13, and then in Stampede 2 in 2017 and 18 as the phases of that machine came up. And now in the new one, Frontera, which I'll mostly going to talk about this machine today, almost entirely, in fact. But it's the result of a very long partnership over about a decade that makes these machines work at scale. And the fact that we've been able to work together for so long has been really a huge part of making that work. And actually, I called this the next generation NSF computing resource. There's actually now a couple of more coming with Expanse and Bridges 2 were just announced, so congratulations to San Diego. I think we got a couple of San Diego folks here. Hey guys. And to Pittsburgh on those new machines as well. So you have a whole host of new NSF supported resources coming online, but Frontera is pretty much here. And so I didn't make the meeting last year to come up and do this, but DK had me come in, for those of you who are here, which I think is about half of you, and do a quick announcement by video. Because he said, don't you have something to announce? And I'm like, well, not really, but if you really want me to. But I was a little busy and couldn't make it up here because I couldn't say anything about the new award last year because there's a sort of vow of silence between when you find out that you have the award and all the paperwork goes through and it becomes official. But to keep track of that operational security, NSF very handily posted this statement on the website 3 months before I was allowed to say anything about the award. And so I showed a slide last year that said, just, you know, I could read the resolution. You can't get in trouble for reading what they post on the website. That they had authorized TACC and the University of Texas to do this acquisition of the new system in response to this proposal. And the other thing I told you, why not just recycle last year's slides? That was last year's slide template. That's the Stampede 2 one instead of the Frontera one. That when those resolutions come out on the website, every media site immediately notices and calls you, but you can't say anything until usually around the last week of September. So we didn't say anything for another couple months after that officially about the award, but it was pretty obvious that something was coming. And so that was a year ago this week when we held MUG last year, and the past year has made a bit of a difference. So I am pleased to say at this point that we have formally started this award, and the machine actually exists for Frontera, and there's a long history of the name as well. It used to be called Frontier. Oak Ridge now has a $600 million machine called Frontier. And so since I didn't have 601 million, we changed our name. So our machine is now Frontera. So same general idea. Frontier should be an NSF name. Computing for the Endless Frontier was the paper that Vannevar Bush sent to President Roosevelt that actually led to the NSF being founded. So I don't know how DOE gets that name, but we'll argue about it later. They have nuclear weapons and bigger budgets, so I know when to draw the line, so occasionally. But yes, so we have a huge team on this award, but notice that there's only one co-PI from not in Texas in the award, and that's DK, because we feel like getting this software layer to work right is critical to making this machine happen. So we're very pleased to have the MVAPICH team basically as full partners now, and the deepest partnership we've ever had around this. And I'll talk about the why, both in my talk, and then some of the performance slides were not ready for the 8:30 talk, but are ready for the 9:30 talk. So you'll see them in DK's talk as well, some of the work they've done on the machine already. But to cut to the chase, there's really sort of 3 parts to this project, and I'll talk a little bit about all 3, but mostly the first one, which is build a big new system this year in Frontera that will deal with the largest challenges. So we're still operating Stampede 2 as part of Exceed, along with Comet and Bridges and a lot of the machines you know. Those sort of face, and all of these challenges are for groundbreaking science, but those are sort of the sort of mid-scale HPC type jobs, if that makes sense, to do high performance, not at the highest performance, but Frontera is really to be focused on the sort of capability class problems. So it has Stampede 2, we have order 2,000 different projects from a couple of thousand different PIs running on that machine. Frontera right now has 37. I expect that will go up to a couple of hundred, but probably never get beyond a couple of hundred. So we want to give people really large chunks of time on this machine and do sort of the broader chunks of time on the Exceed-related machines. So to sort of deal with our largest problems, the ones that we really have to scale up and we're really going to push MVAPICH and the software layers. Obviously, there's a phase where we're going to support and operate this for the next 5 years, and then we're also planning sort of future systems after that, and I'll talk about that a little at the end. So that's been the story, and I've given 45 versions of this talk since last summer over the past year. But now I'm pleased to say that the machine actually exists. A lot of you have spent a lot of time in data centers for various reasons, and I'll get into the physical. This machine is a beast. That's Sean Hempel, who runs a lot of the cables and does a lot of the hardware replacements. If a node used to not work and now it does, Sean probably had something to do with that. But he's about 6'2", and these racks are a lot taller. So they're 3,500 pounds, about 8 feet tall. Getting to that top server is a lot of fun. But it does physically exist now and is in fact number 5 in the world on the top 500 list. It is in fact the largest machine in academia. The 2 DOE machines, Summit and Sierra, at the national labs are up there. The 2 national machines in China are above it, and that's it for machines in the world. All 4 of those machines rely on some form of accelerator to get to their top 500 performance. This is straight CPU performance, so we think it's the largest general purpose machine in the world. As I hope to demonstrate over the next few weeks, there will be a set of problems for which this is without doubt the single fastest machine in the world, particularly those that aren't especially GPU friendly. We don't do a machine like this alone, particularly as we think about planning for the next one. So for our sort of operations phase, it's those of us down in Texas, the team here at Ohio State, folks from Cornell and Texas A&M are all part of our operations phase. And then we think about sort of governance and planning for the next phase of the machine. We have a very broad team of partners from around the country where some of the big science challenges come from, and also a huge team of vendors that are part of it. And I've probably even left some off because we've added IBM to the team as well at this point too. So, but they're apparently all in San Diego, so they won't notice I screwed up the slide today, but I'll fix it by next week. So anyway, a huge team that does this. So let's talk about the hardware, and then if you've seen one of my 45 plus Frontera talks in the last year, you've seen some of these slides, but I have some performance ones that are brand new. And in fact, I haven't shown them to our program officer. So Alan, you can report that I'm showing you stuff that Ed hasn't seen yet. So yeah, he'll be surprised, but he's gonna come see them next week. So again, we're primarily a CPU-based machine. It's actually the peak performance, and I'll talk about why that number both does and doesn't mean anything at all in a few minutes, but it's 39.6 petaflops if you were to do the math on that. So it's a Mellanox HDR and HDR 100, so a mix of 200 gigabit and 100 gigabit links for the fabric. Again, more of that in a fat tree. We have about 50 petabytes of disk and 3 petabytes of flash. If you add up the performance of those two things, we have a little over 1.5 terabytes a second actually running at this speed and measured at this speed, I/O rate, and then some various other subsystems I'll get into in detail around sort of single precision compute and GPU and lots of data movers and API and workflow nodes at this point. So, and this next slide still says Frontier because this was the original picture, but this was sort of our design. That we have one fabric, but multiple compute subsystems, a whole bunch of access, and then a lot of routing to the outside to talk to, among other things, the commercial cloud. And I'll talk about how we interface. Talk a little bit less about cloud benchmarking than I'm into because I just ran out of time to do all this, but we will talk about how we're partnering with the commercial cloud for where it makes sense sort of in our ecosystem. So all those are part of the picture. So let me just dive into the hardware components for a minute. So we have a lot of hardware and tuning type folks here, so we'll get into the detail. So our main partition for compute that the MVAPICH team has become intimately familiar with over the last 2 months is 8008 compute nodes based around the Intel, what's it called now? The Intel 8280 scalable Xeon something processor. Oh, there it is, Intel second generation scalable. Yeah, I put blah, blah, blah on the slide. So they're Cascade Lakes for everybody who knows processors. 28 cores, nominally 2.7 gigahertz, which 2.7 is the modern word for somewhere between 1.6 and 3.5. With the way processor works, it only changes every 50 microseconds or so. So it's very consistent. We have 2933 DIMMs, so we've upped the memory bandwidth some. So if you compare it to Stampede 2, which I've talked about in a couple of keynotes here, we're getting about 15% more core count, 30% more clock rate, about 15% more memory bandwidth. And again, the decision to make this sort of the primary compute is it's universal and it's not an experiment, and all the codes work. When I get into our benchmarks so far, I think it'll illustrate that. So INTERCONNECT is, of course, Mellanox. One of the reasons we're here and talking about MVAPICH. It's a fat tree, so if you'd actually like to know the details, 8008 is 88 times 91. So there's 91 compute racks with 88 nodes in a rack, and with 800 port chassis switches. So if you think about the rack layout, and the new switches now have a 40 port radix, but it's 40 ports at 200 gig. And because we're still PCI Gen 3 on the nodes, you can't really move much more than 100 gigabits over a Gen 3 PCI interface. And doing multiple lanes and using multiple slots is always terrifying. So we're 100 gigabits to the node, so it's effectively an 80 port switch, if you think about it that way. And then we're 200 gigabits to the core, so it's a 40 port switch if you think about it that way. So what we did is took each rack, 88 compute nodes, and put 2 switches in, so logically there are 2 racks there. And by the way, they're called top of rack switches. We have 2 of them in the rack, neither of them are in the top So that's perhaps not the most accurate name, but it's a term of art when you do this stuff. So we use 22 of those 200 gig ports and split them into 44 100 gig ports. So we have 44 nodes going into the top half of the rack, 44 nodes in the bottom half of the rack going into those switches. And then that leaves us 18 200 gig ports. So we're sort of 11 to 9 oversubscribed. But that's a small, really doesn't matter in most of these codes. And then, so we take that 18, which is another great number, all powers of 2 here, which all computing people like, right? 18, 44, wonderful things, and 6. Put a factor of 3 at anything in computing and everyone's head explodes. But so we take those 18 uplink ports and then we have 6 core switches. So we have 3 lines, so 600 gigabits apiece to each of those 6 core switches. So you get about 3.6 terabits to each switch. And then we have no oversubscription from there. So all the core fabric is not oversubscribed, no oversubscription to the storage and the data transfer nodes, et cetera. So that gives us about 8,200 cards, 182 top of rack switches, 6 core switches, 50, 60 miles of cable. Because we can go from 100 on the compute nodes to 200 switch to switch, that means we only had to put in 3,276 fibers. If you've ever had to run one of these, you know that is a wonderful, wonderful thing versus having to do twice that many because you always end up replacing a fair amount. And in this data center, they're 9 feet up to get to them. So it involves scaffolding and other fun things to get to them. And I'm pleased to say we haven't replaced the fibers. And so this is, our 13th sort of large-scale fabric deployment, and in 11 of them we've had to do large-scale cable replacements, and in this one we haven't. So we're very excited about that too. And of course you can't use an interconnect without a software stack, so I'm going to step out of the hardware path for a minute and talk a little bit about the software. In every situation where we put up a new system, again going back to Ranger, you always have to tune your MPI at these new scales, right? It's more nodes, it's more cores. The vendors do a great job of sort of testing at small scale, but this is a $60 million piece of hardware. Probably doesn't surprise you that, say, Mellanox, for instance, doesn't have one at this scale in-house, right? Most of the vendors, even Intel, their biggest internal machines, 200 or 400 nodes. So as soon as you go to 8,000, you find a lot of different ways that it breaks, right? No one's ever seen before. And so you need someone who knows how to fix the stuff that breaks. And so for the last few months, we've been working hard at that. If you want to see specific performance results, I think DK is going to come some, but Hari's here and Amit, and they've been on the machine and tuning, and they can tell you much better than I can about the progress they've been making. There's QMC pack is one of the acceptance codes. I'll go through those in a few minutes, but you see just dramatic improvement from the out-of-the-box performance on those codes once you get through this sort of tuning layer. And once we sort of survive the stand-up, acceptance review for this machine is next week. We rely on the expertise of the team here for a number of other things, runtime introspection, online monitoring. I'm quite confident DK will talk about all these things, auto-tuning, et cetera, and sort of the frontiers of MVAPICH shortly. That's all coming soon. But again, without MVAPICH, we just can't make these fabrics work at this scale. So file systems, let me say a little bit about I/O, because that's always the thorn in our side. We're trying not to do anything. We actually do have a burst buffer at the moment, but the plan is to turn it off. We're doing Lustre and POSIX, and that's it, nothing exotic. So we have 50 petabytes of disk actually spread around 3 file systems. We have 3 petabytes of flash. In 25 years of doing this now, I kind of believe that every user code looks like this when it comes to I/O. So you do a while one, fork, open, close, and usually the close is optional. Most people just leave the files open. There may or may not be work between the open and close, but if so, it's probably writing like 4 bytes. And then you run like 80,000 copies of that at a time. It's I/O can be sort of pathological. We even had a couple of the acceptance codes, which are supposed to be 20 years old and well established, that had essentially this behavior. Based on that experience so far, we used to build giant Lustre file systems, which always became the pain point because the only way to get bandwidth was to throw all the drives we had at one file system and just keep adding drives and capacity until you got to your bandwidth target. So you'd stripe across 4,000, 8,000 drives to build a big file system. And And that was just to scale bandwidth, right? And so that size was not really, as it turns out, bandwidth to the individual users would hardly ever use that full number. So for some it's bandwidth, for other codes it's IOPS. Those pathological ones like the one I showed are really more IOPS limited than bandwidth limited. But we were building one big file system mostly to support the fact that a lot of people were using the file system at once. And if you're really building it to support a lot of people at once, and you think about sort of modern technology where now bandwidth and capacity are basically decoupled, because you can buy flash devices, solid state devices for bandwidth, and you buy drives for capacity. So we don't need to buy a lot of drives to scale bandwidth anymore. So it just doesn't make sense to build a single Lustre file system, given that it's the thing that is most likely to die when somebody runs a code like those previous ones, and that's going to kill everybody on the system. So we just stopped doing it with this one. So we actually have 3 Scratch file systems. If you get on there, there's a Scratch 1, Scratch 2, and Scratch 3, which we're just sort of round-robining people to at the moment. Flash is actually mounted as /flash. It's actually a write through to Scratch 3 at the moment because of the software layer that DDN wanted to use for acceptance, but we'll move away from that over time. It'll be a separate file system. And we only let you on those if you've proven that you're doing something bad to the other file systems. But we have sort of 100 gigabytes a second to the regular Scratch file system, which deals with most individual jobs, and then about 1.2 terabytes on the flash. So, and with 3 homes, 3 Scratches, and the flash, if somebody runs one of these crazy codes that kills the file system, at most you're going to kill 1/7 of the available file systems on the system, and everybody else is going to keep running. And actually we've written some interesting tools where we wrap opens and close. Turns out on our system you can't do more than about an open every 200 milliseconds once you hit a certain threshold, because we wrap it around some sleep calls to keep it from being pathological that way. So we let you do a few hundred a second, which makes everybody else doesn't die. But nonetheless, we're trying to opt into that flash file system, and at least on one acceptance code, it was the difference between passing and failing to have that flash file system there. So a few other subsystems, then we'll get onto what it can do, and this is, we're running out of August, but hopefully next week we're getting the first, we're going to put in a small subsystem around the Optane, which is the 9th name of it, formerly called Apache Pass or Crystal Ridge, or take your pick. Don't call it phase change memory. It just stores bits by using changes in the phase of matter, but it's not phase change memory. I really shouldn't record any of this stuff. But we're adding some nodes around the same Intel 8280 processors that we have in the rest of the machine, with 6 terabytes per node of this non-volatile DIMM. So it's very fast storage or very slow memory, depending on your point of view. With a boot time change, you can bring it up as either memory mapped or as I/O mapped as a block device. But we'll have 6 terabytes per node where we can look at fault tolerance or very large burst buffers or in-memory database. We'll have about 6 terabytes times 16, so about 100 terabytes of capacity in this technology to sort of play with. So we've also added some GPUs in. Things have changed a little bit over time. We took perhaps a less than traditional approach in GPUs here, and that we really liked some of the single precision capabilities just give us much better cost performance type numbers. And if you look at where GPUs really, really excel, and at this point, I'd say probably 65% of the scientific workload can work reasonably well on GPUs, but the things where you get a huge sort of cost advantage are in machine learning and in molecular dynamics, really above anything else. And all of those codes run in single precision, right? Not double precision. But there's a chance that the way AI algorithms are going, double precision will make it back. But we've split our GPU system into 2 components and had some long conversations with NVIDIA about how to license this, which have led to changes in the licenses for everybody. But basically, there'll be 2 GPU subsystems. One that will run, because it's just so different in terms of the binaries you compile and everything else, that will actually run as a separate system that Frontera users will be able to access. It'll mount your file systems, but also have local file systems. But basically, a sort of premier GPU system that looks like the Sierra system at Livermore, where we're using IBM Power 9, because if you're going to buy the high-end GPUs, you need to keep them fed. If you're going to keep them fed, you need NVLink, right? There's no way to do that with Intel or AMD at the moment. So we're using the Power 9 CPUs with 4 GPUs per node, ML and CDR interconnects. We have 112 nodes with 448 GPUs. It does physically exist. We haven't put users on, but it is installed as of July. And we put a separate home and scratch on it. One, because there's some physical distance that would make latency not so much fun, but also because if your binaries are different, and if you give users the same home directory, they will run the wrong binary. We just know this. So you'll see sort of your Frontera home mounted as Frontera home, and then your home will be different. But we'll have that system as well. And then we will have our actual single precision subsystem where we're going to use the desktop class GPUs, actually the workstation class GPUs. So we started looking at the 1080 Ti GPUs, and we prototyped in a system called Maverick 2 at TACC, where we had 24 of these x86 nodes, 4 GPUs apiece, 96. And they say that they'll overheat and they won't run in data centers, but we oil immerse them and they do just fine. So they run fully immersed in a cooling liquid, and they do great. We've run them for 2 years at this point without any problems. And they give you really incredible single precision flops per dollar for the codes that run in single precision, but they don't have the tensor cores and some of the new capabilities. So we've renegotiated with NVIDIA, and we're getting the sort of voltage generation silicon, but in a cheaper card that's single precision optimized with the Quadro 5000s. And so we'll have 360 of those cards. The tanks are in, the cards are just showing up. There was a brief hold up in getting the cards because due to the trade war, the manufacturing of these cards are being moved from mainland China to Taiwan, and that created a supply chain bump in these. So it's probably not going to be September 1st, but before October 1st, we should have all those systems available. So, by the way, this isn't really about data center infrastructure, but this machine uses a lot. Hypothetically, it was going to use 6 megawatts of power. Just the compute power from just the CPUs when we ran LINPACK. We actually measured 59.6 kilowatts per cabinet. So per this much floor space, 59.6 kilowatts, 5,400 kilowatts on the compute nodes. You can tell when we're running LINPACK because the transformers all make different sounds. So if you stand by the transformer and we kick off LINPACK, you can hear it. That's a little bit scary. But so it's a lot of power in. We did use the fastest possible CPU because clock rate just helps everybody. But we think in terms of delivered performance, it's actually the most efficient. But to offset some of that, we're doing direct water cooling into those primary racks. One nice thing about direct cooling the chips we've discovered is you overclock the living daylights out of them. On Stampede 2, when we ran LINPACK, the chips are running at 83C. If you measure the on-chip temperature in Frontera, they run at 50C running LINPACK. So it makes a huge difference in how they run. And how much thermal overhead you can use for other things like speed. And again, we're using immersion cooling in the GPU part. We have a few hundred kilowatts of solar going into it, and we're also buying about a third of the total power from it from wind credits for the rest of it. So we try and, on the one hand, it's a true power hog, but we make it sort of greener on the infrastructure side. Those are actually the chilling pumps for it. Again, for those of you who are students, if you really want to be good at supercomputing, learn a lot about air conditioning. Turns out those things go together. So the never-before-seen slides, let's talk a little bit about, this is what I'm going to show the panel next week around at least the application side of acceptance. When we do acceptance testing, we have a lot of low-level benchmarks. What's every node stream in HPL? What's the point-to-point bandwidth? We use the OSU benchmarks as our MPI acceptance benchmarks. But we also do a lot of full applications, right? Because the real question is not, can the machine meet all these sort of esoteric specs, but can we do real science with it? And how is it as an instrument? So we were constrained in this case by the solicitation to use the SPP benchmark, which was put together for the solicitation that led to Blue Waters, which is the system this is replacing. Blue Waters went online in 2011, but the SPP itself was defined in 2006 when they put out the solicitation around Blue Waters. So that's a 13-year-old set of applications at this point, and worse, a 13-year-old set of problems. So our target when the solicitation came out was to get sort of 2 to 3x the application performance of Blue Waters, at about a third of the budget. So we were looking at sort of a 6 to 9x performance improvement per dollar versus 7 years ago. And there's a lot of ways to measure performance. Per dollar is probably the important one. But so, as it turns out, it's a dozen or so codes with fixed problem sizes. Some of those codes, WRF, MILC, and WChem, are still key science codes and are still being maintained. And new versions are coming up every day, but some of them are closer to obsolete. And we had to go, some haven't been touched in 7 or 8 years. They don't compile with any compiler written in the last 3 or 4 years. They have various and sundry issues, so keep that in mind. And we sort of took all that into account when we were doing the forecasting. But the problem sizes also aren't big enough anymore, right? These were sort of state-of-the-art in 2006. It would be every core on every machine at that point, and they're really not. So in some of them we used a really fairly small part of the machine to hit our targets because the problems just don't scale. There's still some that push us up into around the 250,000 cores range. I think 5,000 nodes was the biggest one we used. So this is the set of codes. We did add Caffe to put one sort of modern machine learning code to it, but the rest were our required ones from the original solicitation. So basically, don't kill me for choice of code. We were stuck with it, and so we have both our target threshold. So the first column is what we forecast. The second column is what we got most of these a month or two ago. There's all sorts of interesting things you do to improve performance over time. So I think if we ran these today, we would actually do better. But given that these are sort of 13-year-old problems and these particular ones are not ones people are run anymore, sort of once we hit the threshold, we stop because we'd rather optimize stuff that's running today than stuff that runs just to get acceptance. But so we have sort of the third column there is the percent over our target that we hit. Fortunately, we passed them all. You can be way under and that's fine, but being even a little bit over, if you miss by 1%, that's a big deal in the way acceptance works. So you want to put in numbers that you're sure you're going to pass but aren't too low to lose to somebody else. So there's a whole art form to setting these numbers. And we came pretty close. You see a couple of them we were within 3 or 4%. And then our improvement over the Blue Waters runtime is there as well for each of those. So our actual throughput is good. And then both the set of nodes we forecast and the number of nodes we actually used. And again, in some cases we had to scale down, things like RMG, pretty old code. We only use 680 nodes out of the 8,000 to hit the target because the problem just doesn't scale up anymore and it's a fixed problem. But again, on an average improvement was about 4.3. And mostly we were pretty close in our projections. There was 1 or 2 that we missed, and I'll talk about why in a second. Missed in a good way. We were way under. You can also look at it again, in terms of our ability to run those problems versus running the same problems on Blue Waters. It was about 4.5 times better. But if you take, again, this bin of applications and all the caveats that go with that, and you look at our per node performance, because that was the number of nodes on Blue Waters that generated those numbers. And then the number of nodes we used on Frontera to generate our sped up numbers. It's a substantially smaller fraction. Well, Blue Waters has 22,000 nodes. So it's not always a fraction, a smaller fraction of the system, but it's certainly a lot less nodes that we throw at it. So sort of node to node, we're about 7.8x the throughput of the Blue Waters machine, which is better than we projected. But I would argue still somewhat disappointing when we think sort of more broadly about where we are in processor architecture and in the industry as a whole, because so Blue Waters was based on the AMD Bulldozer, so that's a 2011 processor technology. We're using Cascade Lake 2019. You want to guess what the peak ratio is between those two processors for that time? So guesses? It's about 16x, right? So I think one of our most fundamental issues, and where performance tuning, Samir's here I know, and various other things are really key, is that we're seeing diminishing returns. Technically we can argue that we're still on the Moore's Law course. Technically we're doubling socket performance every so often in the fixed period, even though that's not what Moore's Law says, but we're still technically doing it, but we're not really seeing it in applications. In fact, this is a little better than I thought we might do, because I've been seeing sort of for every 10x in peak performance, we're getting about 3x in application performance. It's been my numbers. This says we're getting almost half across this mix. But for 16x more peak, we're getting about 7.5x more application throughput, which means peak can keep going up, but if it doesn't infect applications, then why do we do it? It's a little better than I thought because we've only about tripled memory bandwidth in that time frame. So we weren't really as memory limited as we thought. So we got, with only 3x memory bandwidth improvement, we got about 8x across the applications. But again, that was far from uniform. Some are more memory constrained than the others. So all of those numbers I showed, we looked at 4 different MPI stacks to try and do this. And every single one of those is either MVAPICH or the older Intel MPI 18 stack. Especially with these older codes, the MPI 19 stack from Intel just can't run at scale for most of them. And we had sort of the same issues with HPCX from Mellanox and getting at scale. We'll be working with them shortly to sort of tune those up. Because again, the biggest ones were 4,800 nodes, 56 cores per node. A disappointing number of those codes are still pure MPI and are not threaded. So, to launch on 4,800 nodes, you need order 250,000 MPI tasks to launch. And we only have a couple of stacks that can do that. And there's some quirks in various ones, but the one that was way off, if you noticed in that chart, was QMC-PACK, where it ran almost triple the performance that we projected. And again, if you're going to miss, that's the direction to miss in. But you still wonder why your projections are off that much. And it turns out we did all of our forecasting with Stampede 2 around this, because we had Skylake, pretty similar. We had MVAPICH, but we were on OmniPath. And when you dig into QMC-PACK, what we discovered is that there's very, very small messages in that problem related to collectives. There's a lot of all-to-all in that particular code. So if you're running a bunch of all-to-alls and then the average transit message side is just a few tens of bytes, the stacks we were using, and particularly on OmniPath, don't do nearly as well as InfiniBand. In fact, when we went back to one of our QDR InfiniBand machines with MVAPICH and ran a projection from there, and it made what we got on QMC-PACK made a lot more sense. But this is one where the Mellanox InfiniBand just is a lot better than OPA for very small messages, and in this particular code, small messages make a lot of difference. And this is another one where we had to have Hari and team come in and tune in MVAPICH all-to-all performance for these small messages with this many cores, because you have a lot of locality if you're putting 56 MPI tasks on one node, 28 cores per socket, 2 sockets, 56. But it turns out that it's MVAPICH that makes these small messages work. And so suddenly this one is way higher than we expect. And so this is an example of one of the codes. And I didn't get into the comprehensive dive I was going to do into this. But if you were to run this on a network that had a higher than 5 microsecond latency, we're down around 2. But you're probably looking at a 50x performance degradation on it. So these are the kinds of codes when you start to go to scale, hundreds of compute nodes, tens of thousands of MPI tasks, and very fine-grained network traffic that are going to be 50x worse in sort of a commercial cloud environment, even if the single node performance matches what we get in an HPC system. So running a little short on time, and I really don't intend to totally trash DK schedule, although I could if I tried. So I want to say a little bit about our LINPACK number, because I did say we're ranked number 5 in the world. That's all based on LINPACK. LINPACK's sort of a bigger mess even than it used to be. And it used to be quite a mess. And not to denigrate in any way the top 500 list, because I would argue that it's sort of built our industry and been enormously important to all of us. And if you like things like jobs in this business, then the top 500 list has been good to us. But if you go back to Stampede 1, that was when I think we had our last sort of, at least from a LINPACK perspective, and arguably LINPACK isn't the most balanced code because it really focuses on floating point performance over memory bandwidth. But back then, because we had the Knights corners, we submitted a different number that wasn't quite this efficient. But if we just ran the base processors without any accelerators, we'd get 91% of peak at 6,000 nodes on that machine. And so your LINPACK performance and your peak performance were actually correlated. If you look now on the list, you'll find a lot of 50s and 60s. 60 to 65% is sort of typical. But not only has our percent of peak fallen, I would argue that our definition of what peak processors mean, peak performance means, has changed a lot too, right? So It used to be that if you wanted to compute, there was math that underlied things, and so stuff sort of worked. So if you wanted to say what the peak performance of a processor is, you took the clock rate of the processor, you multiplied by the number of sockets, you multiplied by the core count, you multiplied by the vector length, right, how many operations you can do in a cycle, and then you multiply by 2 for a fuse multiply add, because you can do a multiply and an add in the same instruction. And then you multiply that times the number of pipelines in the processor, how many simultaneous instructions you can issue in a cycle. So in Frontera, we'd say it's 2.7 gigahertz with 2 sockets at 28 cores, 8-way vectors, 2 for FMA, 2 issues per cycle, and you say it's 4.8 gigaflops per node. And so 8,008 nodes would be 38.8 petaflops. So that would officially be the peak performance. It's a horrible, horrible lie to say that that is the peak performance, right? But it's never going to change, right? So, first of all, and it lies in both directions, because the headline clock rate you get is not the peak clock rate. We actually can run these chips a lot faster. But you can't run them a lot faster if you do FMAs and 512-bit vectors and 2 issues per cycle, right? By definition, you run at a different frequency in that case, what's called the AVX frequency, or for the or AVX 512 frequency in this case, which is way, way lower than 2.7. Although 38.8 is the theoretical peak, there is no theoretical way to run the theoretical peak, right? Because you cannot achieve that clock rate with that instruction mix, period, in any situation. So, and the actual clock speed nowadays is dynamic, right? It's based on the power envelope, the thermal envelope, and they adjust independently on each socket, and they adjust every millisecond, right? So if we were running a 16,032 socket, hypothetically say, 10-hour LINPACK run, hypothetically say, it's about what it took to get the number that we had, you have 577 billion opportunities for the clock frequency to change on the processor. And it takes many of those opportunities. So again, our clock rate becomes 1.8, and if you sort of do the theoretical fraction around 1.8, we'd get a 25.8 petaflop peak frequency. But that's not right either, because if you can actually keep it cool, right, and you don't run up the thermal limit, and there are various tricks you can do in HPL. For the most part, we don't. We try and leave the chip in the mode that we run for users when we run the benchmark, but you can do crazy things like slow down the RAM. Because if you slow down the RAM, you save 5 watts on driving the pads for those DEM pens, and you can turn those 5 watts into power for AVX. We don't do those kind of games when we run it, but you can. It's in the tuning manual. And there's about 500 other of these little things that'll get you 1 or 2%. But as it turns out, because we were running at 50 degrees C, a fair amount of the time in our LINPACK run, we were actually running over the AVX frequency because it was turboing up, because it was cool enough and had enough free power. So 38.8 is not right, 25.8 isn't either. But no one's going to say a machine that you can theoretically say is 38.8 is actually 25.8, right? That's just never going to happen, right? In terms of the way they market the chips, et cetera. And this is not Intel specific, right? Any vendor, and there's versions of this for every chip out there. So percent of peak is yet another sort of meaningless metric for how we tune systems that's changed a lot in the last few years. So I'll tell you, we put in a number about 22, which if you think of as a peak of, if you think of 25.8 as the peak, it's a pretty high percentage of peak. I think we could have gotten 23 out of it, as clean as the system is now. But it turns out the number 5, the old number 5 was 21, and the old number 4 was 61. So as soon as we hit 21 and a half, I'm like, yeah, we're done. Let's do real science. I mean, enough time spent on that. But we probably could have gotten 23 out of the machine. But take that with all the appropriate grains of salt. So that's all great. What are we really doing with the machine, right? That's all hardware, that's benchmarking, that's important, but we are actually running science on it. So in late May, once we finished the sort of LINPACK runs, we started, things were still a bit of a mess, so we began hand-running codes on behalf of users. By the start of July, we would let users on at 256 nodes. As Hari will show you, we now let them on at 1,000 nodes. And going up, but we make them benchmark on 1,000 before they request more. So we've gone to, getting closer and closer to perfect, because day one, we're just never perfect on these systems. And it's a much longer talk about all the different things that got fixed. over that. But today we have 37 science projects running on the machine, producing new results. The very first one was a group from Utah, and this is one of the hand-run ones we did, but it was a very large Hari Sundar there in general relativity code that does some interesting adaptive mesh. And this is one, there's so much rebalancing. It's not particularly GPU friendly with Dinjo GR, and it allows you to do, because the mesh is so much finer, we can model smaller collisions than you can in the LIGO project. For the very sort of massive black hole collisions they're looking at, you can look at sort of just 2 or 3 solar masses with this code colliding with another one. So that was our first run. Apparently it's in the deck twice, or stuff's, oh, yeah. There's some evolution of black hole collisions if you'd really like to see them. Skip that for now, but we have a whole bunch of other things. Manuela is also, she's also works with the LIGO team in gravitational waves, so another astronomy problem, but this is out of Rochester. And again, they're doing some of the largest, most accurate runs they have ever done around this on the machine already at much faster than they used to do. There's a lot of detail on some of these. We have Peter Casson at the University of Virginia on a more health-oriented one, looking at sort of viral structure and via atomic interaction, designing new antiviral therapies for what they're doing. Again, 2 to 3 times faster than the old machines, just sort of out of the box for them. Talks a little bit about how it affects his postdocs and scientists to hit that. We have Ganesh over at Lehigh, who's doing some PV materials, photovoltaic type work, and a bunch of next generation, and talks in particular, he's one of the teams that came out, and we sort of sat down with them and did multi-core tuning and some other things, and they're seeing 4 and 5x even in the early science period in terms of what they're doing to do better photovoltaics. Olix's work is kind of interesting, so all of these are interesting, obviously, so you know, we're sort of glossing through some really groundbreaking science here, but this is trying to apply AI into quantum chemistry, which many people are still skeptical about. I am both skeptical and think there's something there at the same time at the moment. So we have to be very careful about removing physical constraints from our models as we start to apply AI to them. But there are some really sort of amazing things happen. But we're seeing more and more users who are combining machine learning techniques in some way with the actual physical simulations, either in pruning ensembles or in you know, for the most part, we're trying to not throw out the physics and just say black box neural nets will solve things. There's so many dangers in doing that I can't even begin, but they've sort of inferred their wave equations here from neural nets. And in this case, they're doing some of the things through like the force field descriptions via neural net and AI learning, and still putting physical constraints back into the model. Put it so, and they set the record for what they've ever been able to do for their group, and he's super excited about AI. I'm a little more cautious at this point, calls it a Sputnik moment. But nonetheless, there's some very interesting things happening as we're blending AI and machine learning. That's also an entirely separate talk, but this is one of the early users who are tackling that. And then George threw one UT Austin user in here, so, and mostly people around the world, but and George is interesting. I mean, so again, there's very important cancer work here, looking at gliomas and some machine learning. But George sort of does a pretty complicated end-to-end workflow, right? He has some CPU-intensive stuff. He has some GPU-intensive stuff. He does a lot of viz and analysis. There's some machine learning. There's some traditional modeling and more traditional image recognition. As he's, you know, comparing MRI scans to predicted. And you know, shared file systems, and he really likes sort of the integration across things. So, so good things happening there. And so I have just a couple of minutes left. So let me say 2 last things. One is that we are actually partnering with Google, Microsoft, and Amazon in this project to try and not do burst mode computing, not do, oh, we can just augment the machine with the cloud. Because we think for most of the problems, like the ones I just showed that we run on there, we're going to outpace the commercial cloud, both in terms of cost effectiveness and just raw performance, by a pretty hefty margin. But that doesn't mean there isn't a space for the commercial cloud in computing. We think there's actually a pretty substantial space there. So we want to use the cloud where the cloud works in partnership with HPC and not make it sort of an either-or competition. So, and the first three things you will see there, one is publishing data and being able to sustain your data set in the public cloud. So if you want to put up a portal with data and analysis, and we do have some in-house ways to do that, but we'll support, sort of one button push, and your data will go out to Amazon and live there, and you can do things on it, Google and Microsoft as well. We also like the sort of notion of combined workflows. If you need to do a bunch of natural language processing on the front end or image tagging on the front end of your workflow, there's such good services tuned for that in the cloud. We're putting web service layers on top of this machine. You ought to just combine that through a web service workflow and use the existing services. So we think we'll see some very interesting hybrid workflows. And the other thing they do a lot better than us is, deploy thousands of nodes every month. So they have every new node technology out there for evaluation. Tensor processors, FPGAs, at a much higher cadence than we can ever support. So we can evaluate the base node technologies through the cloud. And so we have partnerships based on those three things. They're not all quite there yet on day one, but we're working through the credentials issues. So data publication will be first. We'll put a portal in front of the machine. You can go to your Frontera portal, pick data you have in homework and Scratch, and do a little bit of curation. We'll issue you a DOI, and we'll push your data out to the commercial cloud to sort of sustain it, and we'll pay the bill for a while with your allocation, and then eventually hand it to you, which makes my life easier too. So, and again, you'll be able to get, I think the first thing will be TPU access in terms of new node evaluation that's coming up, because we have no other way to get those. So, given time constraints, I won't talk about containers and protected data and some of the support we do. I do want to just make a quick comment that we are responsible for some planning around phase 2 for what NSF is calling the Leadership Class Computing Facility. And I vow today to you to find a better name sometime in the next 5 years. So I'll do my very best. So instead of LCCF, but so the sort of task for LCCF is to move computing into the way that NSF funds the other big instruments like LIGO, like the Large Hadron Collider, like the ice cutters, like the big telescopes, through what's called MREFC, the Major Research Equipment Facilities Construction Fund. A bit of a mouthful. If you don't know acronyms like MREFC, CDR, PDR, FDR, LCCF, you may want to keep it that way because your life will be cleaner and you'll sleep better at night. So don't worry about what any of those things mean, but there's a lot of reviews to get through to do this kind of thing. But the idea is, one, it creates sort of a more sustainable funding base for how we'll do computing at the NSF in the future. And the idea is by 2024 or so, when Frontera wraps up, maybe 2025, we'll have something that can do 10x that capability of future science problems. And all we have to do is define what capability means, what science problems mean, and what computing facility means in that time frame. So other than the fact that all the words are undefined, we have a very clear picture of what we'll be doing in 2024 and 25. It also helps that none of the vendors really have a clue what processors are going to look like in 24 and 25. So we'll do part of this design from evaluation of what people use, from building new prototype systems and things like that. But a lot of the design is going to come from input from the community. So the sort of last thing I'd like to ask everybody for, since you're all part of the HPC community here, and you see a lot of different users, different ones than we see, et cetera, is to get your input. And so we'll have a whole bunch of formal activities. There'll be LCCF planning workshops that you'll see. They're assuming they accepted a BOF at SC19 and things like that. There'll be online surveys, there'll be interviews, et cetera, et cetera. But really, if you want to give me feedback, just give me feedback. Email me, call me, catch me in the corner at lunch. I show up places, or anyone from TACC. But we want to get input from everybody in what this looks like. So, again, it's 4 or 5 years to do the planning, to put this out, and to create, a larger scale NSF program in computing that will have a decade plus after Frontera. But even though it's a long process, things start to take shape. We have documents due starting in about 9 months. So feedback needs to come soon and quickly. So I encourage all of you to reach out and give me feedback either through the formal channels or any others. So given that I am really, in fact, out of time, let me just say thank you to the NSF that supports all this work, for Frontera and for all the systems that led up to Frontera to make this happen, and to our many, many partners, and certainly all of our users. And leave you with my favorite computational science quote, and like all things in supercomputing, it comes from 1812. So when really the heyday of supercomputing in a lot of ways. And I stole this slide from David Keyes, I will admit, but Humphrey Davy invented electrochemistry. And because of that, he added like a row to the periodic table by himself, right? So he did amazing contributions to science. But he being a more humble guy than me or anyone in HPC, he said, and he has a much more eloquent way of saying this, but he's like, it's not really the fact that I was smarter than everybody else. It's that I had a new tool. I had a tool that no one had before, and because I had these new tools, I was able to do new things. Now, in his case, he invented the tool, so he should get more credit. But we think he was probably really talking about Frontera, right, to give people this new tool to do that kind of science. So with that, let me just say thank you, and if there's time, I can take some questions.